Hello! This has been a little bit of a comedy of errors on my end, but that's okay. You won't know the difference, except I just told you, we're restarting. Welcome to Analysis 1B's lesson. This is the lesson that you need to watch and think through a little bit. Prior to your September 8th or September 9th class, there is no school on Monday, September 7th. So a B day is going to be the 8th, and an A day is going to be the 9th. This is for Analysis 1B. Our topic for the day is that students will be able to, number one, we're going to review some polar curves. We're going to review polar a little bit. It's been a while. You did this back in pre-cal or in functions. Two, we're going to use some calculus to be able to compute the area involving shapes defined by polar curves, right? So as you know, area is going to relate to integrals. It's really about the fundamental theorem of calculus, that we have Riemann sums, which then, thanks to the FTC, we can use anti-differentiation to help us solve. And three, I'm not sure why I spaced it so tight together. Oh well, three is examples. Examples. I cannot spell while talking. That is okay. So that's our plan for the day. Let's do a bit of a review of polar, and then into the calculus part. Okay. Starting off polar, right? So if you really remember polar well anyway, speed this part up. That's okay. For polar graphing in this course, and as you've done in the past, we're going to be thinking of that r is some function of theta, that a radius out from the center point is some function depending on the angle of sweep starting at the positive x-axis, also known as the polar axis. So were I to draw a coordinate plane, we can think of this point as xy, as how far in this direction you go, the translation, how far up you go. But we could also think of this as r theta, in which case we would be saying how far out from the pole, how far out from the origin, and how far around theta. What angle have you swept out? And from this, if you drop a perpendicular and think of that right triangle, just a little bit of trig reminds you of the relationships that we care about, that the x-coordinate would be the same as the radius times sine of the angle theta, that the y-coordinate, I'm so sorry, cosine of course, cosine, that the y-coordinate goes with r of sine theta, and we could go the other way if we needed to. The r there, the length from the origin, is the hypotenuse of that triangle, so r squared would be x squared plus y squared, you could solve for r, and for theta you could use any trig identity you want. My personal preference is to express the relationship with theta in terms of tangent, and you just have to be careful about which quadrant you're in. But that's okay. From this, an important step that you took next with your exploration of polar was to think about some certain shapes. So I'm actually going to start by listing out some various equations that represent shapes that we are familiar with, that we're going to use some more, and then we'll back up and mention what shapes they are, right? My hope is that as I mention these, you have some recollection of what's going on, or that if not, maybe you'd pause for a couple minutes and you kind of think about what shapes these would make. I'm going to do one as a demo, but just the one. So those three kind of go together. That's all one kind of shape. We can have the case of that radius is some real number a plus or minus the same number a times cosine of theta, or sine of theta for that matter. Another one we're going to think about is when r is some a plus or minus a different number instead. And also it could be cosine or sine, that's okay. Let me put a line across there. There we go. Another one we can think about is when our radius is equal to some constant times cosine and then a factor inside the trig function. Again, this could be sine or cosine, but some scale factor of theta. And finally, we're not really going to work with this one much for calculus right now, but just for completion's sake, let me remind you that there was a shape you worked with of the form r squared was some a squared sine of 2 theta, or cosine of 2 theta. Let's look at, say, this one, a plus a cosine theta. Let's do a little sketch, remind ourselves how that works. I'll move it aside. And then I'll bring back the other sheet and we'll actually talk about which shapes they all are. So as an example that we could do, let's talk about r equals just 1 plus cosine theta, right? Why not? 1 plus 1 cosine theta. So recall, when graphing in polar, this inner ring is all a uniform radius 1. The outer ring is right now a uniform radius of 2. So that's going to help us plot things. When theta is 0, cosine of theta is, of course, 1. So the radius would be 2. So along the angle of 0, I have a point at radius 2. At the angle of pi over 2, we have 1 plus 0. So we'd be at a radius of 1. At the angle of pi, we would have 1 plus negative 1. So in this ray of angle pi, my distance is actually 0. So I actually stay at the origin. And for 3 pi over 2, of course, we'd get 0 again. 1 plus 0 is a radius of 1. And this might be enough. That might be enough to kind of jog your memory and you remember the shape. But if not, it's okay. We can add a few more, right? Cosine of pi over 3 is a half. So I'm going to use that. So the angle of pi over 3 is, say, roughly here-ish, give or take. And so 1 plus a half, I'd be out there, and I have a point there. At 2 pi over 3, which is, say, roughly there, cosine is negative a half. 1 plus negative a half gives me a half. So I go out a radius of a half. And similarly for 4 pi over 3, for 5 pi over 3. And now hopefully that's enough points to jog your memory a little bit. And if it isn't, that's okay. Means you have a little review to do, but that's okay. The shape curves around and does something like that, right? There's our shape. So let's go back and recall, therefore, that this shape is a cardioid. Cardioid. Back to the beginning. If r is a constant, that means I don't care what radius I'm at. It's always just a uniform distance from the center. Well, that's the definition of a circle, right? Being a uniform distance from the center. And indeed, these other two are also circles. They're just not centered at the origin anymore. Something to think about. If you've forgotten, that's okay. Similar to a cardioid, but when a and b can be different, when the coefficients can be different, are our limicons. Lima with a like fancy C, French C. Think French. I'm pretty sure it's French, not Italian. Not actually 100% sure about that. A limicon. And depending on the relationships between A and B, we could get a loop, we could get a dimple, or we could have a case of neither of those things, right? So a loop, limicon, or a dimple, or neither. Over here, the key factor is, usually for a trig function, your period is 2 pi. So from theta being 0 to theta being 2 pi is one rotation of this shape, right? Is going around once and repeating what you've done after that. But if this n were, say, 2, then by the time theta is pi, I'm doing a cosine of 2 pi, which is the end of the period. We start repeating already. And that may be enough for you to remember. You may need to think about it a little bit more, but that's okay. We get roses, right? We get petals because of that change to the periodicity of the situation. N helps you define how many petals in your rose, right? Whether you have an even or odd n. Even n doubles, in fact, the number of petals. Something to think about. And finally, one that we're not going to do much with right now, but a lemniscate was the last big category of shape that you worked with. A lemniscate. So you should at least have some continued familiarity of these. You might be a little rusty, and I'm okay with that, but we're going to need to work with something, right? If we're going to do calculus. These are the shapes we're going to be working with. Just so you have some more examples in mind. So my sort of goal with the following list is you should be able to think through these a little bit and get a rough sketch of the shape, right? Not all the details, but you should be able to remember the general situation happening here. So let me just list some, and if you're really kind of at a loss, if you're not remembering, that's okay. You just might need to spend a little more time thinking about these shapes and figuring out how to decide what they should be. So one option is that our radius is 3 sine theta, right? No problem. Or we could be talking about when our radius is 5 minus 10 sine theta. That's something we could work with. Or we could want to consider the shape when our radius is 3 minus 2 cosine theta, right? Another one we could think about. Or another option worth considering is when our radius is just 5. A shape we should be familiar with. Or perhaps our radius is 2 plus 2 sine theta. A shape we want to work with. Oh, I realized I'd omitted an important one last time. I'm glad I had to remake this because I screwed something else up. R is, say, let's do 3 cosine of 3 theta is one you might want to have to think about a little bit. And then I'm going to do 2 special cases sort of at the bottom here, which are a little different than the rest of these forms that we've worked with. One would be, let's mark them as special cases. Special. If R is just, say, 2 theta. So it depends on an angle, but there's no trig involved. It's an interesting shape to think about. And then another interesting one to think about would be, what if instead of defining R at all, what if R is free? What if R can be anything, but theta is known to be a constant? So those are kind of newish special situations. You study them a little bit, but not quite the same sort of category of shape, even though it's also in polar. So again, the goal here is you should be able to get a rough idea of these different shapes, right? A sense of sketching what they should look like. And if you had to do them exactly, you could if you had to. And that is the review of being able to make things. We're going to review one tool that we need when working with polar, which is the idea of working with intersections in polar. Intersections in polar. So for example, let's think about the case of finding intersections of the circle where R is always 2, and the limicon where R is 1 plus 2 cosine theta. Where R is 1 plus 2 cosine theta. And if we were to sketch this, I should have used different colors. Sorry, I really should have thought of that. One of them is quite easy to sketch, right? If R is 2, that's just a circle of radius 2, no problem. There is a circle of radius 2. This is R equals 2. The other situation we have to worry about here, though, 1 plus 2 cosine theta. So let's plot some points if we need to and think about it, right? When theta is 0, we get 1, so it's 3. So it'd start out here. By the time we get to pi over 2, we're going straight up. 0 here, so it's only a radius of 1. And we know that this is a limicon, so we already know the rough shape. Some more points if you want, or you don't have to if you don't want to. By the time we get to theta equals pi, it's negative, so negative 2. So 1 minus 2 is negative. So if this is the positive radius direction, negative would point the other direction, right? Something you remember. So this is going to have a loop. We are going to come around and then switch and go inside. At 3 pi over 2, we have a 0 again, so a total radius of 1. And here's where I need to back up and think about some stuff. Let me check where I hit the origin, right? So I can figure out where my loop really starts. 0 is the radius for 1 plus 2 cosine theta. So that would be that cosine theta is negative 1 divided by 2, so negative 1/2. For which, between 0 and 2 pi at least, I get 2 pi over 3 and 4 pi over 3. So I can kind of map those out, and those are the points where I hit 0 again. So I start at angle 0, and my angle changes until my angle has hit pi over 2. And then by the time my angle is 2 pi over 3, I've hit the origin. And that's how my loop starts. There's my loop. And then I come back out the other way, right? And just kind of looking at this now, we can identify 2 spots where we expect to have intersections. And if I was careful graphing instead of just sketching, things would look much more symmetric. The catch, which I hope, again, you have some recollection of, is that just because it looks like a polar intersection doesn't mean it's actually an algebraic intersection. There may not be a coordinate pair, r comma theta, that works for both graphs at once. If you are wondering about that sort of thing, then as a quick aside, consider the graphs of r equals 5 and r equals negative 5. Think about what those graphs look like in polar, but I'll guarantee off the bat, right, there is no ordered pair r comma theta that satisfies both at once, because r has to be 5 for one of them and negative 5 for the other. 5 does not equal negative 5. So it looks like there are intersections, but in fact there are no algebraic points in common. Geometric points in common, it looks like they overlap, but algebraically there's no simultaneous solution to the equations. The same thing can happen in general, so we do have to be careful. If I wanted to find intersections, I'd use some algebra, and I'd set them equal, right? No big deal. 2 equals 1 plus 2 cosine theta. Move it over, that's a 1, divide, so we get the cosine theta is a half, which tells me that I expect to have intersections at theta is pi over 3 and 5 pi over 3, which, sanity check, that seems reasonable. Remember that I sketched, right? This brown point at the top does not look like it's at an angle of pi over 3, but it was only a sketch. It certainly could be, right? If I'd curved my line maybe a little more accurately, it's plausible. And that's enough to confirm that the algebra is reasonable. The r value, we don't even need to do any computation, right? If theta is pi over 3, well, the r value better be 2, because for the top equation, r is always 2. So from this, we get 2 points of intersection. The point of r is 2, theta is pi over 3, and the point of r is 2, theta is 5 pi over 3. Thus concludes the review of polar. So those who were kind of fast forwarding a little bit through the review of polar, now is when you might want to consider slowing the video back down to regular time or 1.25 maybe. Because we're going to continue with new stuff. Okay, continuing with new stuff. Let me grab the correct notes for this new stuff, which I now have. Excellent. Think about what we did when we were finding area in Cartesian, area in rectangular. We started with the concept of having a graph, and we did a Riemann sum, right? So we partitioned up our region, we made boxes, and we literally added up the areas of boxes. For some graph, y equals f of x, 1, we partitioned the x interval of interest. 2, we made rectangles. Make rectangles. And the area of those rectangles was some difference in x, some width multiplied by some height. F of xi star, what was that? For a given rectangle, remember that the height could have been the left endpoint or the right endpoint or some point in the middle. It doesn't actually matter, right? It's a Riemann sum any way you do it. So xi star meaning that in the ith rectangle, it's some x value. But it could be any x value in the ith rectangle. To be super formal, I really should have a sub I here too as well. Because as you remember, we often used rectangles of equal width, right? A partition of equal width. That's called a regular partition. But we didn't have to. The partition doesn't have to be the same width for each box. So the width of the ith box and the height at some point in that ith interval. 3, we summed these up, and 4, we took a limit. And specifically our limit was as the widths went to 0, right? As each box width went to 0. More commonly, we talked about the number of boxes going to infinity, which for a regular partition, an even partition, is the same thing. But for an irregular partition, it doesn't have to be. Width going to 0 is really what matters most, right? The widths of each box. But in practice, use a regular partition, the boxes go to infinity. We're going to do the exact same thing. The exact same thing. But we're doing a polar graph instead. So this time, think about a curve that for some angle, maybe starting at an angle here, has some radius. And then the radius can change as the angle changes, right? So for any given angle, I have a certain radius, but that radius changes as I move. So this is a polar graph. Let's think about what a polar version of a rectangle would mean, right? We're going to follow these same steps. Before we partitioned x, now we're going to partition theta. Now we'll partition theta. but it's the same idea. So if I'm interested in starting at this theta and finding the area from this theta all the way around to that theta, ooh, whoops, oh well, we're going to get little bits of theta. So maybe from this theta I until this theta I plus 1, right? This difference there would be a delta theta. Step 2, we're going to make rectangles. Okay, well, they're not rectangles anymore. Now they look like this. Now they are sectors. And the question is, what is their area? We've got to figure that out. So we need before it was easy, right? A rectangle was width times height. Now we need some way to figure out the area of this like snow cone looking shape, this spike looking shape. It's very, very roughly kind of triangular, but it's not really, right? Because at the base here, it's curvy. So, step 3, by the way, is still going to be sum, exactly the same. Step 4 is going to be a limit, exactly the same. Our task is to figure out what this area of a sector is. So, let's start with what if it was actually a circle? So if we were using a circle specifically, and I had this chunk of circle, so I had this amount of delta theta. Well, that's no big deal, right? We can just do a ratio. So the area of the sector divided by the area of the entire circle should be the same as the amount of angle we're using divided by the total angle, which is, of course, 2 pi radians. I also know the area of the circle. The area of the circle would be pi r squared. So the area we actually care about, area of the sector, over pi r squared would be delta theta divided by 2 pi. We do a little multiplication. The pi's actually cancel. That's kind of cool. And we get 1/2 times r squared times delta theta. The area of a sector of a circle. The area of a sector of a circle. There is a slight flaw here, though, right? Because our actual shape isn't a circle, so it doesn't have a constant radius out at the edge here. But this same concept is where we're going to go with this. So let me draw the more complicated version that still uses the same sort of approach, still uses the same sort of rules. If we have some curvy thing, so that I'm using that and this. What I want to note here is, I'm going to call this one this time just theta 1 and theta 2 to make life a little easier instead of using I and I plus 1. My width down here is still delta theta, right? The width of angle I'm working with. But this time, we have to think about the fact that we have, say, an inner radius. That's supposed to be all the same radius, bear with me. And an outer radius. That's really rough. Sorry about that. Maybe more like that. That's okay. An inner and outer radius, right? So that this inner radius has a value of r equals, r1 equals f of theta 1. And this outer radius, I'm so sorry, by the way, if anyone's red-green colorblind. I think I remember to ask my class, but I haven't checked with Mr. Kirk's. I do apologize. I will have to double check on that for the future. But we have an inner radius and outer radius. The inner radius, the way I drew it at least, depends on the value of r at theta 1, and the outer radius depends on the value of r at theta 2. So we actually have 2 different areas that we're working with here. We have the area of the inner sector, which would be 1/2 times pi times the inner radius, f of theta 1 squared. Oh, I'm so sorry. Do I want to keep this? Do I want to re-express it? Yeah. All right, let's use what we used last time. I was kind of mixing up. I was thinking I should do the entire part times the ratio of angle we care about, right? Pi r squared times, I want delta theta out of the 2 pi total. So let's actually do it that way. Let's make it clear. So this would be the entire inner circle, but the part of it I care about, the proportion of it I care about, is the proportion of the angle I want over the total radians in a circle, which becomes 1/2 f of theta 1 squared delta theta. The area of the outer sector based on this situation would be the area of that entire circle, pi f of theta 2 squared, pi radius squared, times the amount of that circle I care about, the proportion of it, the angle I care about over the total angle, which is 1/2 times f of theta 2 squared, delta theta. And here's the big catch. Here's the big catch. The inner area that we're using is definitely less area than the actual real area we care about, which is in turn less than the outer area. Right? No problem. Let me add a little picture there just to make it more clear. For our actual shape, we have something like this, and then something that curves like this, and something that meets it like that. And the inner circle is that red part, and it leaves out the extra bit. On the other hand, for the outer circle, we have a radius out to there, and then it curves up, and then a radius up to there. And the green part extends beyond and includes that extra piece outside of it, right? Inner area less than the real area, less than the outer area. And here's where the calculus comes back into play. There are 3 sort of real broad, very difficult to prove, but very, very useful theorems that you learned in Analysis 1A. You also learned some other really important theorems, like, say, the fundamental theorem of calculus, right? But I mean more like foundational than that. And that's the extreme value theorem, the intermediate value theorem, and the mean value theorem. Those 3 theorems are particularly useful for helping with other proofs. And that's what we're going to use for one of these things, right? I'm claiming that I have 1/2 f of theta 1 squared delta theta, and that's less than the real area I want, which is less than 1/2 f of theta 2 all quantity squared delta theta. And I make the following claims. That 1, the radius function, f of theta, is continuous. And 2, area is continuous. Right? The area function just depends on the f function anyway. It's just f times some other constants. So if f is continuous, area is also continuous. And therefore, by the intermediate value theorem, there exists some, not quite what I want, some theta star between theta 1 and theta 2 such that the real area is precisely equal to 1/2 f of that special theta squared delta theta. Because the real value of area lies between area at theta 1 and area at theta 2, there is an angle between them that the real area is equal to, right? If I use that angle between them, the value I get is the same as the real area. Cool. How useful. How useful. Since we have a bound on either side of the real area is some value between them. So in the function of 1/2 times f of theta squared times this width, whatever it is, there is some angle between theta 1 and theta 2, where if I plug that angle in, I get exactly the real area. I don't know what angle that is, but I know there is one. It's there somewhere. It's there somewhere. And that goes all the way back to the same idea as using xi star. In a Riemann sum, you can use any value you want inside the interval of the box you're working with. Well, this angle from the intermediate value theorem, theta star, is some angle between theta 1 and theta 2. It's an angle in the box we're doing. So when I set up my Riemann sum, I'm going to set it up thinking of this angle. I still don't know what it is. I don't need to evaluate it, right? I don't need to compute what it is. But I can set up my sum in that way. So we end up claiming that the area inside a polar curve, it's not really between the curve and the x-axis anymore, right? Because it starts at the origin and extends out until you hit the curve. So the area inside a polar curve is approximately the sum over the boxes, which are really sectors, of 1/2 f of some theta I star for each interval. The intermediate value theorem says there's some angle you could use, times the widths of the sectors. So how do we make this better? How do we make our approximation an actual value? Same way we always have, we take a limit, right? So we get that area is the limit as the biggest width goes to 0, or boxes to infinity, right? That's really what we tend to think. More and more sectors of the sum of all of the boxes, 1/2 f of theta I star, that special theta from the intermediate value theorem, times the widths. And as our final step, what I want to note is, well, the fact that theta is our variable doesn't matter for calculus. Calculus looks at this and says, boxes going to infinity, sum the boxes, a formula with a variable. A formula based on the variable and widths based on the variable. So I don't care that it's a theta instead of anything else. This is an integral. This is the integral from the start to the end angle of 1/2 f of theta squared d theta. The fact that it's a theta instead of an x doesn't matter, right? A limit of a Riemann sum becomes an integral. And notice it's commonly written, this f of theta is itself the radius function, right? So it's common to pull out the 1/2. I'll do one last. Pull out the 1/2 and do an integral from alpha to beta of r squared d theta, where we just understand, we remember that this r is actually some theta stuff. It's not a variable by itself. It's dependent on theta. But this is kind of shorthand for the situation, right? 1/2 times the integral from the start to the end of the radius function, d theta. So there's our setup. There's our derivation of area inside a polar curve. Example time. Let's do some very specific problems. I have 3 in mind, but I'm actually going to add a 4th. I'm going to do example 0 as our first example. Okay? So here's example 0. I always like to start with a shape that we absolutely already know the area for. We can make sure we didn't do anything horrifically wrong. So let's say that our radius is 3. That's a circle of radius 3 we know for sure the area better be pi r squared, which is 9 pi. We claim from our derivation that area is, I'm going to go all the way around the circle. So 1/2 times the integral from angle 0 to angle 2 pi, I've gone around the circle, of the radius function, which is 3 squared, d theta. So that's a 9, and as you know, of course, the antiderivative of a constant, so we get 1/2 times just 9 theta, evaluated from 0 to 2 pi, right? The antiderivative of 9 would be 9 theta, and then we use the fundamental theorem of calculus. I'm going to actually pull the 9 out also and just leave it as a 9/2 sitting out there, and I get 2 pi minus 0. The 2's cancel, and indeed 9 pi, as we knew it had to be. Right? It better work. So there's our example. There's our example. Example number 1. Example number 1. A little more complicated. Very doable. You've got this, but a little more complicated. Example 1. Let's use the shape r equals cosine of 2 theta. Cosine of 2 theta. Which, remember, is a rose. Because n is even, it has double the petals. So it has 4 petals. And the way I like to keep track of orientation is just to check something, right? When theta is 0, the radius is 1. So I have a petal that starts out here at radius 1. And then I know it's 4 petals, so I know it's equally spaced. I know how this works now. So I have a shape that looks like... that was terrible. I have a shape that looks like that, right? It's a sketch, not a graph. It's a sketch. It's okay. All right? If I want, I could find the area inside this shape, the area inside this rose. We know our formula. The area would be 1/2 times the integral going all the way around the rose of cosine 2 theta squared, d theta. And that's fine. We can do this. But look at the shape for a sec. Looks to me like there are 4 petals that are all the same. So how about instead of doing the entire thing from 0 to 2 pi, how about we just do one of the petals and then multiply by 4, right? That seems easier. Well, one of the petals would involve bounds of, say, negative pi over 4 up to pi over 4, right? And we could do one of the petals that way, or we could have gone from pi over 4 to 3 pi over 4. I mean, it's whatever we want. We could do one petal and multiply by 4. But wait. Look at one of those petals. One of those petals itself has a symmetry, right? So how about instead of an entire petal, how about we only do this blue part of the petal from 0 to pi over 4, double it for one petal, multiply by 4 for everything. So we're going to be doing this part, right? Just that little blue part inside that one piece. Notice, for a given angle, the radius starts at 0 and extends out until, hey, look, I hit the shape, right? So what I'm going to do instead of the entire thing is I'm going to say the area of the entire shape is 4 petals times 2 halves times 1/2 of the integral from 0 only up to pi over 4 of cosine of 2 theta quantity squared. I strongly recommend using symmetry when you're trying to find areas in polar. It helps. It helps. And then there's one last trick to worry about here, which is that we know that cosine squared of phi is equal to 1 plus cosine of 2 phi divided by 2. Which means if I replace every phi with 2 theta, let phi equal 2 theta, no, theta, sorry, not pi, let phi equal 2 theta, we can sub this in and see what happens. So my area is 8 times 1/2 times the integral from 0 to pi over 4 times, I have another 1/2, 1 plus cosine of 4 theta, d theta. And that is an integral that you can do now. I'd pull out the half and then deal with 1 and deal with cosine of 4 theta, right? But that's an integral you can do. And I'm going to stop there. I'm not going to finish that computation. This actually would be a great place to insert a question if we're doing that in Canvas and have you evaluate that. So there's example 1. There's example 1. Here is example 2. I'm going to use two shapes. I'm going to have an inside curve. The inside will be that r is 3 sine theta, and an outside curve, where the outside curve is 1 plus sine theta. So we know the top one is a circle. We can get some points if we need to get an idea of it, or you can remember how to convert it. Fun fact, multiply by r and then convert to Cartesian. It's a good way to know what shape it is. But I know a rough sketch, right? I'm not going to worry about every detail. I just want a rough sketch. The top one is a circle that extends along the y-axis. Instead of being centered at the origin, that's what that sign is going to do to us. So there's the top one. And the second shape is a cardioid. Since it's sine, it also kind of uses the y-axis. Sine and y relate together, so that's kind of its center. When theta is 0, it's a radius of 1. By the time theta is pi over 2, it's its maximum radius, right? A radius of 2. And notice this top one goes out to 3. So it's going to have a point there maybe. And it's going to have started about here. And it's going to kind of circle up and come in as the heart-shaped cardioid, right? And I want the area that's inside the circle. Is this really what I wanted? Yeah, inside the circle but outside the cardioid. So I want this part. Inside the circle, but outside the cardioid. This next line, this very next thing I'm about to draw, I'm trying to choose a color that I think will work for people. Let's just use black. We'll use black. This next thing I'm going to draw is the secret to everything. Okay, this is the way to do things. This is the secret. I'm going to kind of pick an arbitrary angle and look at what happens along that angle. So here's an angle that I picked. And what I notice is, I don't care what's happening here. I start caring on the cardioid. That's where I start to care. And I keep caring until the circle. I don't care until the cardioid. I keep caring until the circle. This is the same idea in Cartesian as if we had a graph with one function up here, another function down here. I could call that f, I could call this g. And if I want the area between f and g, we would pick an x value, and I would start looking above it. I don't care until g, I keep caring until f, and then I don't care anymore. We know here that the area is the integral of f minus the integral of g. From a to b, right? We'd have bounds, but same thing up top. So we now have the concept that what we want to do is, our plan is an integral involving the circle minus an integral involving the cardioid, right? That's our plan. We need the details, but that's our plan. So what are the steps we're doing in this problem? Number 1, we sketch. It doesn't have to be a perfect graph. It just needs to be a rough sketch so you can kind of get that sense of where do we start caring and where do we stop caring. Step 2, what we haven't figured out yet is where to set our bounds. Notice that if I picked an angle down here, I wouldn't care ever, right? It's just totally irrelevant to me. I start caring at that intersection, and I have shape going around on my angle, going around an arc until that intersection on that side, right? So from here to there, and that arc is what I care about. And to get that arc, we need the intersection values, right? We need the intersection. Intersections. All right, let's do that. So to get our intersections, we need to set these equal. So I have that 3, so this is step 2 right now. Step 2 right now. We get that 3 sine of theta needs to equal 1 plus sine of theta, which is that 2 sine of theta is 1, so sine of theta is a half. So theta is pi over 6 and 5 pi over 6. And now suddenly you realize why we made you do speed trig. Here's why. I don't want you to have to spend a lot of time focusing on this, right? I want you to focus on the calculus. And same for Kirk, of course, right? Does it feel plausible based on our sketch? Yes, this is plausible, right? Have an intersection around here somewhere, an intersection on the other side. All right, good. Step 3, you might think that step 3 is setting up the integral. But no, it's me, Dio. Whatever. That's probably more groan-worthy than funny at this point. Who cares? No, step 3 is not set up the integral. Not quite yet. Step 3 is stop and think. Stop and think. Hey, look at the shape. There's something very important to notice about the shape. What do you notice about that brown area we care about? Inside the circle, but outside the cardioid. Yes, good job. Symmetry. Right? So let's not go all the way across. Let's do twice the area of pi over 6 until pi over 2, right? Instead of going all the way across. Anytime you should use symmetry, use symmetry. Okay? Step 4, I'm running out of space. I'm so sorry. Step 4. Step 4. This is really where I would generally suggest draw those black radii, right? So draw radii. This is where you decide what integrals to actually set up. I just wanted to talk about that in the beginning as our general plan. Draw radii. So pick a radius and draw it, and notice I start caring at the cardioid, I stop caring at the circle, just like in Cartesian, if I might start caring at G and stop caring at F, right? Same idea. Caring meaning where is the area that I actually want to measure. There is a step 5. There is a step 5, which is evaluate. Evaluate. And there are our steps. Sketch, find the intersections, stop and think, draw the radii, and evaluate. And this really bothers me now, right? Because imperative verb phrase, command, imperative verb, and intersections. I'm so sorry. That should say, like, find intersections, but too late. So with this in mind, let's set this up. Let's actually do it. We know our bounds. We know our plan, so we can set up the rest. I have an integral from pi over 6 until pi over 2 of 1/2 times the circle radius squared d theta, and I'll subtract from that the integral from pi over 6 to pi over 2 of 1/2 times the cardioid radius squared d theta. And now we evaluate, right? And now we evaluate. Personally, I do a little arithmetic first, and then what I would probably use is that cosine of 2 theta, among other options, is 2 sine squared theta minus 1, so that I could get sine squared theta. This is stuff with cosine of 2 theta. And I'd probably do that substitution and then use that to evaluate, right? Power reducing formulas are very important, very useful for these kind of problems. Power reducing. So that we can get rid of the square, right? Just to point out real quick, right, as an aside, one might think that the integral of sine squared theta d theta should be something like sine cubed of theta over 3, maybe. Let's see. Or maybe it's cosine cubed, right? Because sine and cosine relate to each other, so maybe that would make sense. No. No, no, no. Try derivatives of these. You do not get sine squared. There is a very important reason you don't get sine squared. There is a rule that you have learned that is the justification of why you don't get sine squared. Why not? You should make sure that you agree and are confident that the derivatives of these things are not sine squared. Okay? That's why we have to use power reducing. So there's example 2. Notice again, I'm not actually doing the eval right now. That you know how to do. I'm doing the setup part. Last example. We have about 10 minutes to make an hour. And again, like, the examples are kind of up to you how much you want to pay attention. So you can kind of fast forward through them if you're confident. Play on 2 speed or something, 2x speed if you're that confident. But if you really want to watch and go through it in detail with me, that's great too. And I'm happy to offer you that option, right? I'm happy to offer you that option. Example 3. Final example. Example 3. I want the area between, which is to say inside one but outside the other. R equals 2, and R equals 4 cosine of 2 theta. So we know from example 1 and earlier, right? This is going to be a rose with 4 petals. It's going to have the center of one of the petals along the x-axis, because we're using cosine. And of course, we have a circle. So we can sketch again. We have a circle out here at radius 2. My green marker is not doing great right now. The largest radius I have for my petals goes all the way out to 4. And I still have to fit 4 petals around, right? So one of my petals does this, and one of my petals does that, and then a petal down here, and a petal over there. So the part between these two, the part that's inside both, would be the region, I'm trying to think of what might be a good color for people, having not checked colorblind, I'm so sorry again, would be like this part, right? This part is between both. Between is kind of ambiguous, right? Ambiguous. It'd be better to say inside both, right? I have to be inside the circle while also simultaneously inside the rose. And I point this out. I use the term between because it's common for textbooks and problems to say between when really it's not a very good description, right? Really, we mean inside both right now. Okay? Just to be clear. I'm going to take that one little bit of picture, though, and I'm going to blow it up bigger. I want to make sure you can see something that's very important. So I'm going to take this, I'm going to draw the same thing bigger, okay? And the idea is this. I still have an axis coming through, and the other axis would just be here. And I have a circle that's kind of doing this. And I have the other shape that's doing this. And the between part, I really hope I drew that well enough to show you what I'm trying to show you. The between part is here, right? Okay. What do we need? Step 1, sketch, right? Let's go back. Step 1, sketch, we did it. Step 2, intersections. We're going to come back to this picture. We're going to come back to it. Let's do intersections in the meantime, though. We have 2 equals 4 cosine of 2 theta. So cosine of 2 theta is 1/2. So 2 theta together, cosine is 1/2 at pi over 3. Also at negative pi over 3 in this case, right? Those are the ones I care about. Also at lots of other points all the way around. But what I care about right now, I can kind of look at my sketch to identify where do I care. And I care at pi over 3 and maybe at negative pi over 3. Which means theta is going to be pi over 6 and negative pi over 6. Right away, notice I only bothered with 1 petal. We're going to do 1 petal and multiply by 4 again. The sketch lets you figure that part out, right? So 1 petal, we're going to multiply by 4 again. And we're also not really going to do 1 petal. We are in the stop and think stage. Not only can I do 1 petal and multiply by 4, I don't need this whole petal. So in our stop and think stage, what we're actually going to do is 4 petals times 2 halves times an integral from 0 to pi over 6. No, I shouldn't write that. That was a terrible idea. Please ignore the last 10 seconds. 2/2 times 0 until pi over 6. I'm going to write it that way, okay? The region we care about goes from 0 until pi over 6. Yes? Good. Step 4, draw radii. So I'm going to draw radii now. Let's draw radii. I'm going to pick one, and I'm going to draw, and here's a radius. And it looks to me like I start at 0, and I go until the circle. And I never use the rows, right? Like that interval there doesn't use the rows at all. Something's weird. Let's draw some more, right? I could have another here. That doesn't use the rows either. And another that doesn't use the rows either. And I could keep drawing them until I hit this intersection point. That is at pi over 6. But that's not the whole shape. I still have this sliver in here, right? I have not accounted for this sliver yet if I stop at pi over 6. And also, everything from 0 to pi over 6, I only ever hit the circle. The rows was totally irrelevant. Here is why the stop and think sort of stage and the draw radii stage, I was getting more paper, by the way, that's why the volume got quiet for a sec. The stop and think stage and the draw radii stage are so vitally important. I'm going to draw this again and exaggerate, okay? We have theta is 0, and we have a circle to here, and then we have a rose to here. So this part is the rose, this part is the circle. I have radii going out to the circle until I hit pi over 6. And my radii after that go to the rows, right? Drawing my radii. So we're not actually doing 0 to pi over 6. That wasn't quite right. We did need the intersection. We needed to know where we switch from the circle to the rows. So now we can get our plan, right? From drawing the radii, we can get our plan. We're going to do an integral from 0 to pi over 6 for the circle. And we're going to add to that doing an integral from pi over 6 until we got to figure it out. I don't know why I'm capitalizing rows but not circle. Let me capitalize circle there too. Of the rows. Here's our plan. When do we want to stop? Well, if we look at our radii, we stop when the radius just hits 0. So this is going to be roses r is 0. Roses radius is 0. Which is 4 cosine of 2 theta is 0, which means that 2 theta should probably be pi over 2. That's where cosine gives you 0. So theta is pi over 4. And again, let's go back to the big sketch. Is it plausible that as I come around this petal, I get to the origin at the angle pi over 4? And yeah, that looks plausible, right? That kind of splits the difference between those two petals. That makes sense to me. Pi over 4 would kind of be there, right? Here's pi over 4. So that seems plausible. There's our sanity check. So what's our actual integral that we're actually doing? Our area is 1/2 the integral from 0 to pi over 6 of the circle's radius, which was 2 squared, d theta, plus 1/2, I noticed a mistake. Let's see if you notice it. But I noticed a mistake. I'll fix it in a sec. It's not a big deal, which is why I'm not stopping yet. 1/2 from pi over 6 until pi over 4 of the rows, which had been 4 cosine 2 theta squared d theta. Did you catch the mistake yet? This is the area I've drawn on this piece of paper. This is half of a petal, and then we have 4 copies of it, right? This is just this piece right here. I need to double it and then quadruple it. So this wasn't actually the area, it was actually an eighth of the area. And then we can get the total area that way. Thus concludes, oh wow, that was exactly the 1 hour mark as I said thus concludes. Thus concludes the lesson. As I always like to do, I'm going to run through the slides at the end. Our plan today, we reviewed polar curves, we derived area and polar, and we did 4 examples, in fact. A review of polar and a review of polar shapes, including how to go about sketching it, if you've forgotten, and some shapes that you should be able to kind of recognize. You should be able to look at one of these and kind of think fairly quickly, not immediately maybe, but fairly quickly what shape it is. These are kind of special. You might want to think about them. They're cool. Talk about how to get intersections, the idea that we might have to worry about, and aside, we might have to worry about, is it a real intersection algebraically, or only it looks like one? We talk about getting intersections. We used what we already knew about finding area in Cartesian, and we modified it in purple for area in polar. Same concept, same steps, we just have to reinterpret. Sectors instead of rectangles. How do we get area? Here's how we get area. This is the area of a sector. But if we're working with a messy shape that isn't a perfect sector, isn't a perfect circle, it's a little more complicated. So we introduced the inner part and the outer part, and then we applied the intermediate value theorem to claim there is some angle that gives us exactly the right area. Don't know what it is, but it's there. And that's the angle we use when applying our Riemann sum and limit thereof to come to an integral, right? Here is the formula for an area inside a polar curve. Our first example, example 0, was a shape we already know very well, a circle of radius 3. Formula worked, good news. Our second example, we talked about the idea of using symmetry and using a power-reducing formula, and we didn't finish evaluating, right? We set this up, but we didn't evaluate the whole thing. Next example, we talked about the idea of inside one shape but outside another, and we developed this sort of plan of how to go about it. We need a sketch. We need to find some intersection points. We want to stop and think about the situation. We're going to draw radii to help us think about the situation. And with all of that information, we set up and finally evaluate. We use symmetry. We related it to the idea of the area between two curves. And then here was the setup and introducing the idea of power reducing. Careful with your integration. Finally, our last example, the area, we called it between, but we really meant inside both. I just want you to be aware that people use some ambiguous language for this sort of problem sometimes. We sketched. We found intersections. We had an idea, but then as we were drawing radii, we realized that idea isn't complete. We don't want to stop at the intersection in this problem. It's that part of it only ever uses the circle, and the other part only ever uses the rows. So we had 2 separate pieces that we needed to add together. And thus concludes your lesson in polar area.